So we'll carry on now with the second part of the lecture on probability. And as I stated in the first lecture, if we're going to do subsurface modeling, we're going to use probabilities because of uncertainty, and we're going to use probabilities to support decision making. We have to understand fundamental concepts of probability, make sure that we understand probability well. And so what we'll do now is we'll get into a discussion. We've already covered frequentist concepts, and we're now going to get into the Bayesian approach. As we introduced it before, with the Bayesian approach, we allow for, or we acknowledge the role of belief, expert belief, experience-based belief, not just willy-nilly belief, but a strong sense of how experience and expertise can help us with judging. Now, we also acknowledge the fact that we will formulate a probability and we will be willing to update with new information. And so Bayesian statistics allows for belief, it allows for updating with new information. Now, the cool thing is that we got ourselves into this Bayesian situation by building up from frequentist concepts. Specifically, we had identified previously that we have a product rule. And that rule is that the joint probability can be solved for as a conditional. So the joint B and A, B intersection with A, is equal to the probability conditional A given B times the marginal probability of B. Now, of course, it makes sense that you should be able to reverse these, of course. You should be able to say, okay, probability of joint B and A, and describe it like this, and we should be able to talk about the probability of A and B and describe it like this. It's pretty trivial. Now, it makes sense too that the joint probability B and A is equal to the same or equal to the joint probability of A and B. So if this is true, then we can take this relationship right here, substitute the right-hand sides for each, and we get this form right here. We've combined two product rules together to get what's widely known as Bayes' theorem. And so this is a very powerful relationship. It can be used for a wide variety of problems. But let me just kind of divert just a little bit and make a little bit more comments about why we might appreciate Bayesian statistics. At the beginning of the last lecture on frequentist approaches, I made the comment that it's best for us to keep both of them in our back pocket and be ready to switch, to pivot, to move Bayesian or frequentist perspective depending on the problem. That's because there's many classes of problems which are much more amiable to Bayesian versus frequentist or vice versa. So we want to be able to use the type of framework or perspective that helps us solve the problem best. So let's just try to justify or think about Bayesian statistics. When would we want to use a Bayesian approach? And so we mentioned already that it's probabilities based on degree of belief in an event occurring. We update with new information that's available, and we'll say that there's problems we can solve with it that we could not solve with frequentist approaches. In the book by Savai, 1996, on Bayesian statistics, a really, really nice book, the first chapter has excellent descriptions around motivation for working Bayesian approaches. And they pose this problem. They say, what is the mass of Jupiter? And so you'd imagine, how would the two perspectives solve this problem? If you were a frequentist, you would say you would measure the mass of enough Jupiter-like planets from multiple solar systems so you could build up a distribution and work out the probability based on that. Now, of course, you got to remember 1996, I believe, was prior to exoplanet discoveries. And so at this point, of course, we'd recognize that there's not really that ability to try to count your way to solve that problem by pooling multiple Jupiters, or Jupiter-like planets, I should say. The Bayesian approach for this would be you would build a prior probability using some expert knowledge or experience, and that probability could be quite naive. There's many cases in which we use almost completely naive priors. We acknowledge the fact that we have very little information. And then we'd update with any available information, indirect measures that could be used to infer something about the mass of Jupiter. The problem would become much more tractable using that construct or that perspective. So let's go back to Bayes' theorem. And so we showed it before. It was just a combination of two product rules where we just reverse the joint. We put them together, and of course we can reorganize it. We simply take the probability B marginal from this side, divide by both sides, and now it's in the denominator on the other side. This is a very common form of Bayes' theorem that's used to solve a wide variety of different problems. In fact, one way I like to think about it is that this method allows us to flip the conditional probability. Often we find ourselves in a circumstance where we're able to calculate the probability of B given A, but the probability of A given B would be very hard to get to, very hard to calculate without a relationship like this. And so it allows us to move from one conditional probability to the other. Now that's one way to think about it. Another way is you think about it in the terms of updating. And in that case, we're talking about this probability of A as being known as the prior. That's the information that you have based on experience, belief, and so forth before you gather the new information. Then you have likelihood, probability of B given A. This is the new information that you add with the new data that you've sampled or gathered, new information that's been provided in some manner. You are then updating the prior with the likelihood to get to a posterior. The posterior is now telling you the probability of A given you now had B information to update it. Now the evidence term is interesting. It's the probability of B. In general, the evidence term is so often hard to calculate. We'll show problems for which we can calculate it. In many cases, it's seen more as a term to ensure, it's a standardization to ensure closure, to ensure that the probabilities sum to 1. Now, so the common expression for Bayes' theorem is based on this form that I showed, the prior product with the likelihood, divided by the evidence term is giving you a posterior. A really cool way to think about this, and it solves a lot of problems, is imagine that you have a probability based on a model. Then you have some type of new information. So now you're looking at the probability of new data given the model. You're standardizing by the probability of that new data. And then you are calculating the probability of the model updated now with that new data. That's a very good way to view the Bayesian updating approach with Bayes' theorem. So as we mentioned before, this is all symmetric. You could have the alternative form where you have the probability of A given B or the probability of B given A. Nevertheless, I did mention before that it is a bit of a challenge to get at the evidence term, the probability A or the probability B, depending on the form we're looking at. But we can use all of the probability concepts that we've learned up until now in order to make a substitution to be able to calculate this probability. So we know that the probability of A is equal to the probability of A plus B, or the probability of A and B, plus the probability of A and not B. So if that holds, then we can expand using the product rule this joint probability into this conditional times the marginal, conditional times the marginal. And while it may look much longer and maybe unwieldy, it is often much easier to get these terms right here and be able to solve for the probability of A. What are we going to do with Bayes' theorem? What is that class of problems beyond measuring the mass of Jupiter that we would have encountered within our jobs and modeling the subsurface, which would be useful, which this methodology would be powerful and useful? And so let's take it like this. Let's take a couple of examples of some unique circumstances and then we'll generalize. Event A, you have a disease. The disease could be something rare, maybe a cancer, maybe it's not so rare. Event B is you test positive for the disease. Could you agree that that's not the same thing? Having the disease and testing positive for the disease are two different things. Which one is of greater interest to you? Which one do you know? Well, you may know you test positive for the disease, but you have quite certainly much more interested to know if you actually do have the disease or not. Let's take it to subsurface. There's a fault that's compartmentalizing your reservoir. Event B would be the geologist says there's a fault. Low permeability in a sample. Event B would be the laboratory measure is low. Do you see the pattern here? The generalization would be that we have a circumstance in which we have, it looks like something's happening, and we want to know if that thing is happening. We have evidence it's happening. We want to know if it, in fact, is happening. In all these cases, we want to calculate the probability of something happening, given that it looks like it's happening. It looks like it's actually happening. And so what do we have? Well, it'd be very difficult to calculate that probability directly. But we often have the probability of the thing happening. We often have the probability it looks like it's happening given it's happening. Often with a test, we'll know about its accuracy and being able to detect the problem if it's there. And we also have a probability that it looks like it's happening. We can solve for that using the expanded form of the denominator we showed before, where we're combining the joints, probability of B and A, probability of B complement and A. Okay, so let's expand this out and talk about a little bit more, and then we'll look at a problem. So this is the general form. Now, what's very interesting about it is that you can immediately look at it and recognize some parts to it. You recognize that the top here is the correct detection rate. It looks like it's happening given it's actually happening. This is the occurrence rate, the rate at which it's actually happening, and this is the old detection rate. The probability that it looks like it's happening, false positives and true positives. Now, so we can expand the form out and start solving some problems. Let's go ahead and solve one of these problems together. I'll leave another one for you to complete. Your prior information has cite that suggests that a channel feature exists at a given location with a probability of 60%. We decide to further investigate this with using seismic data. So we're going to shoot new seismic. The seismic survey can show this feature is present with 90% probability if it really is present. Is not present with a 70% probability if it's not really there. So what have we been provided? Well, the probability prior, the probability that the channel feature is there, is going to be known as the probability of A. A is the feature is present. B is the seismic shows it's present, and then we have the complements. A would be the feature is not present. B complement is the seismic does not show the feature. Okay, so we have the probability of A. We know that there's a 60% chance that the feature is there. That's our prior. If it's present, our true detection rate is 90% probability that the test will say it's present. So probability of B, the test saying it's there, given it is there, is 90%. We also know that the probability that it will show that the test will show that it's not there, given it's not there, the true negative result, is 70%. So will the seismic be useful? So now we have to calculate a couple more probabilities, and then we can populate this equation. The first one we need is we need to know the probability of a true detection given it's not there. Now the cool thing is we were given the probability of not detecting given it's not there. A true-false result was 70%. By closure, remember closure with the conditional probabilities, we can calculate the probability of it being detected given it's not there as 1 minus the probability of it not being detected given it's not there. Now we can also use closure here because we need the probability of the feature not being there. Well, we said 60% likelihood for the feature to be there, so we have a 40% probability that it's not there. And of course we can populate this equation, the expanded form, with all of those probabilities. They weren't too hard to get to, and these were things we readily have within this problem. We populate the problem and we can take a new look at it with some new eyes and say, that's kind of interesting. The top part, the numerator, is in fact the true positive rate. The feature being there and being detected. We repeat the true positive rate here. That's the feature being there and it's detected. And this is the false positive rate. The feature not being there, but we detect it too. So this is very interesting. So the probability of the feature being there, given we have a positive test indicating it's there, is equal to the true positive rate divided by the true positive plus the false positives. And that makes a lot of rational sense. Now, what does it come out to be? 82%. So in this case, we had a 60% prior probability. With the new information, we update to 82%. That's pretty useful. That we have now significantly increased our certainty of the channel feature being there, and that feature might be really important when it comes to the reservoir. I want to show this example right here. It's worked out for you, but then I'll leave it for you to work out, but I want to point out one interesting feature of this problem. If you look at this problem, what you'll find is the probability of a crack being the blowout preventer, given that you have a test for the crack that indicates it's there, is only 4.7%. Now, that's a very low probability. In fact, you might wonder about the value of the test at that point, because the test saying the crack is there, only 4% chance, 5% chance rounding up, that it's likely to be there. And so we got to be concerned about that. What happened? What went wrong? Well, the problem is that you have a combination of a very highly unlikely event. Cracks only occur about 1 out of 1,000 times. And you have a high false positive rate, 2% of the time. So what happens? You get swamped by false positives because you have such a high rate of it not happening, and many of those will be misidentified as happening, 2% of those. And so that's what happens. Now, another way to put it, though, or to think about it, is your prior probability was very low. And if you think about it, this is a huge information add because you've gone from 1 out of 1,000 chance or probability of the crack being there to 5% chance of the crack being there, probably helping you determine that you need to take another look. And so there is information to add, but you still do have a relatively low probability given a positive test. Now, there's a whole variety of different problems you can solve with Bayesian approaches. Here's another one right here I put in here for completeness. I took this directly from Wikipedia. I thought it was a great example. I'll leave this to you to work out. They're available here for you. Similar types of problems. And I also provide a bit more comments around a general form of the Bayes theorem for specific cases where you have exhaustive, non-overlapping events and so forth. You're welcome to look at that. And with that, I'm going to conclude my discussion for now about Bayesian statistics. I hope what you can see is that it's very powerful, useful when we're talking about updating with new information. You'll find very quickly we're going to have a variety of different workflows developed for the subsurface that will in fact use a combination of frequentist and Bayesian approaches. That is very powerful when you're able to switch or pivot between the two frames of reference in order to solve a wide variety of different problems. So that's it for my discussion about Bayesian statistics for now. I hope this was useful to you. I'm Michael Perch. I'm an associate professor at the University of Texas at Austin, even wearing my burnt orange today. And I'm always happy to discuss. If you have questions, go ahead, fire off a question in the comments. I'll answer them when I get to them. And also, I'm Geostats Guy on Twitter. I put out a lot of resources and so forth. I also do a lot of training and teaching inside of a variety of companies and organizations and professional communities. And so I'm always welcome to come out and help out with training, teaching, workflow development, consulting, and so forth. All right. Take care.